Hello, my name is Jester. This is my Lab 3 report. So the purpose of this lab was two parts, and the first one was finding the mass. That's the title of it, and it's just using motion data to determine the mass of the black hole by analyzing the star's orbit and applying Newton's laws of motion and gravity. Then the second part of the orbit or the lab was the orbit don't crash part, and it was to simulate the gravitational interactions between a planet and its moon and a spaceship to determine the initial velocity needed for the spaceship to achieve a stable figure-8 orbit influenced or figure-8 orbit influenced by both the planet and the moon. So some of the principles of this lab were Newton's law, the law of universal gravitation, which you can see here is F1 is equal to F2, which is equal to G times M1 and M2 all over R squared. And then with much of these other laws, with like perpendicular, with momentum and perpendicular force, and parallel forces, and then like update positions or position update formula and the velocity update formula. So some of the takeaways of the slide. So when I when we the mass of the black hole that I found in the first part was 1.3 times 10 to the 34 kilograms per. And then initial velocity was the 2.59 times 10 to the 4 the x and same in the y meters per second. That was basically found by trial and error. And so some of the assumptions that we made in this lab was that gravity is the only force acting on these objects. There could have been other forces or other gravities from like distant planets that change the real motion in real life, in real outer space, and also that the black hole doesn't move. That was an assumption that it doesn't move. So in real life they do move, and that could change variables in the motion, and also that Newton's laws are valid throughout. And so for code one, or for the coding of part one, we took the system. Well, the system was the star, and the surroundings was the black hole. And so you can see this is like kind of my like the first picture on the left is the like system properties and initial conditions. Then on the right are all the formulas we had to calculate and put in for it all to work out. So I'm going to play the code for that one. That's what it looks like. All those numbers generating are like the masses of the black hole. There we go. Beautiful. And so this was the second part. This is code for it. So the system and the second part was a spaceship, and the surroundings were the planet and the moon. So you can see same initial or very similar initial conditions. And then here's the like at the very top, there's the ship speed in the y and the x direction, and then also the rest of those formulas we had to plug in to make the code work. So here is that. And this one will run for a while, so I'm not gonna watch the whole thing, but just does that. And I couldn't get it to get into the figure-8 motion. That was very hard, and a lot of guessing did not work. So for possible error calculations or marginal error, the rounding off error, we like a lot of the numbers got rounded off. They weren't exact, so that definitely, if there was any room for error, a lot of it could have come there. And also we ignored non-gravity forces and like gravity forces that we didn't like account for. And then here's the discussion. So for the what if, about like this imaginary system is a black hole, star, planet, moon. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? I said we had to consider all the body masses as dynamic masses, like moving instead of not point masses, like not in a single spot, and also include all the gravitational forces we left out. So all the forces that in real life that really other like masses that can change it. And for the what does it mean? Like we said, or I said, the net force on an object equals the rate of change of its momentum. The components show different effects. The parallel component changes the speed of the object's speed with perpendicular component changes direction when mass is constant, these components of a force and momentum change are identical. However, if mass changes, such as in rocket losing fuel, the rate of change of momentum differs from the net force because it also includes the effect of mass changing. Smiling. Thank you.